Every data structure explained in 18 minutes. Data structures are the backbone of software and the essential infrastructure behind modern AI systems. In this video, we're going to break down the essential data structures you need to know for both general programming and machine learning. Arrays. Let's start with the array, which is the oldest and simplest and most important data structure in all of programming. Arrays are a fundamental data structure used in programming to store multiple values of the same data type in a single variable. Each value in an array is called an element, and every element is assigned an index, which is just a number. An array is a fixed block of contiguous memory, meaning its elements are stored side by side in memory. Each element is numbered starting from index 0. Why 0 and not 1, you ask? Well, because the index just tells the computer how many steps to move from the start, and the first element is 0 steps away. In machine learning, everything you feed a model gets turned into arrays. By extension, a matrix is just an array that's arranged into rows and columns. And a tensor is the same idea stretched into even more dimensions, such as a color image which needs height, width, plus 3 color channels. In an array, since everything is lined up with numbers, the computer can jump straight to any element in the array instantly. This means grabbing item number 1047 out of 1,000,000 is just as fast as grabbing item number 2. This is called O of 1 access, or constant time. But there's a downside. The size of an array is fixed. This means that if you ever need more room, the computer needs to grab a bigger block of memory and copy every single item over. Secondly, inserting or deleting in the middle of the array is slow, because every subsequent item in the array needs to shift one step to the right. The time it takes to do this is known as O of n, or linear time. Basically, arrays are great when you mostly just need to read the data, but it's painfully slow when you're constantly adding and removing things, which is exactly what our next data structure was born to solve. Next up are linked lists. A linked list is a data structure that's used to store a collection of elements, but it does it quite differently than an array does. Instead of the elements sitting next to each other in memory, they can sit anywhere in memory. Each element, which in a linked list is called a node, contains 2 parts, the data and a reference or pointer to the next node in the sequence. Because linked lists do not store elements in continuous memory locations, this allows them to grow or shrink dynamically as needed. This makes inserting and deleting elements incredibly fast, which essentially solves the problem that arrays have. So you might ask yourself, why not just use linked lists instead of arrays? Well, this fast insertion speed comes with the opposite trade-off from the array, in that accessing an element in a linked list is much slower than it is in an array. Because there's no index in a linked list node, the only way to access the node is to start at the very first node and follow the pointers one by one until you get to the desired node. You can imagine if the linked list has thousands of nodes, this is problematic. So whether you use an array or linked lists depends on your use case. If you mostly are just reading data or need instant access by position, use an array. If you're constantly inserting or deleting items, then use a linked list. Now for the stack, probably one of the easiest data structures you'll ever learn. A stack is a linear data structure that stores elements in a last in, first out order, meaning that the last item added is the first one removed. Elements are added to the top of the stack using an operation called push, and they're removed from the top with an operation called pop. That's it. And because both these operations happens at one end, the time it takes to push and pop is O of 1 constant time. Conceptually, you use stacks every day. You know when you hit the back button on your browser? Well, that's a stack of web pages. Ever delete something you're typing accidentally? Well, that command plus Z is literally a stack of your actions. More importantly, every program you've ever run uses a call stack. This means each time a function calls another function, the computer pushes it onto a stack, and when a function finishes, it gets popped off. If you've ever heard the term stack overflow, it's basically when this call stack runs out of room. In machine learning, a great example of a stack is backpropagation. When you train a machine learning model, it records the operations from the forward pass, and then walks back through them in reverse order to compute gradients. A perfect last in, first out pattern. Next up is the queue data structure. This one is the stack's mirror image, a structure where the first one in is the first one out. Elements are inserted at the rear of the queue, pause, using an operation called enqueue, and removed from the front using a dequeue operation. And just like the stack, the operations are O of one constant time, because all the action happens at one end. Queues are everywhere in computing. Your printer processes documents in a queue, streaming services buffer video frames in a queue, and web servers handle incoming requests in a queue as well. By extension, there's also a beefed up version called the Deques, which is a double-ended queue where you can add and remove from both ends. In machine learning, AI agents often store its recent experiences on Deques, so that old memories fall off one end as new ones come in on the other. Queues also power data loading pipelines. While your GPU is busy training on one batch, the next batch lines up in a queue waiting their turn, so the GPU never sits idle. The hash map. A hash map is a data structure that stores data as key value pairs, where each unique key is associated with a specific value. It uses a hash function to convert each key into an index in an internal array, which allows data to be stored and retrieved very quickly. This makes operations such as inserting, searching, and deleting elements highly efficient, averaging at constant time. Occasionally, however, two keys hash to the same slot. That's called a collision. The classic fix to this is called chaining, where instead of one value, each slot holds a small linked list, so colliding entries just get added to the chain. When you look up a key, you hash to the slot, then walk that short list to find your exact match. A quick variation worth mentioning is the hash set, which is the same idea of hash maps minus the values. It stores unique elements and automatically prevents duplicate values, which makes it perfect for anything where uniqueness matters. Hash maps are everywhere. Python dictionaries and JavaScript objects are hash maps, and they're in machine learning too. For instance, every large language model tokenizer is essentially a giant hash map converting words to token IDs. So basically, every prompt you've ever typed into ChatGPT went through a hash map before the model ever saw it. Understanding these foundations is exactly how you move from just using AI tools to actually building them. This is why I created my newsletter, The Gradient Descent. Once a week, I take a machine learning concept and I break it down in a way that actually makes sense. No complicated lectures, just clear, digestible lessons to make you actually get it. But it goes beyond just reading. Every week you get 3 things: a hands-on collab so you can literally code in Python through guided exercises, weekly practice assessments with fully explained solutions, and visual cheat sheets for every weekly concept with illustrated explanations and Python code snippets. For example, take supervised learning, where all of the machine learning models are organized neatly for you in one diagram, along with the commonly used code. Oh, and when you sign up, you also get a free ebook, Machine Learning Simplified, which is essentially everything you need to understand about machine learning from the ground up. Yours just for joining.
Damn, son.
Click the link below to try it free for 7 days, where you will have everything I mentioned sent directly to your email. Now, back to data structures. Next up is the tree data structure. I figured we should start branching out. Anyways, a tree is a hierarchical data structure made up of nodes connected by these lines called edges, with a single starting node called the root. Each node can have 0 or more child nodes, and the nodes at the very bottom with no children are called leaf nodes. Trees are commonly used to represent anything with hierarchy. For example, your file system, organizational charts, or HTML documents. The star of the family is the binary search tree, which is a tree with 2 simple rules. Rule number 1 is that every node has at most 2 children. Rule number 2 is that the node with smaller value goes on the left, and the larger value on the right. These 2 simple changes makes searching through the tree brilliantly fast. For example, let's say we have a binary search tree that holds the value 50 at the root, with 30 and 70 below it, and 20 and 40 under the 30. Let's say we want to find 40. We start at 50, the root node, and since 40 is smaller than 50, we know to go left. Once we hit left, we know 40 is bigger, so we go right. And boom, we found 40. 3 steps is all it took, and we didn't need to look at every single node. The time it takes to do this is known as O of log n, or logarithmic time, which isn't quite as fast as the hash map's constant time, but still faster than linear time. In machine learning, entire models are based on the tree data structure, such as decision trees, random forests, and XGBoost. Next is the heap data structure, which is another tree data structure, but with one important rule. Every parent is more important than its children, or vice versa. When every parent is less than or equal to its children, that's called a min heap, where the smallest item in the whole structure sits at the root. In a max heap, where each parent is greater than or equal to its children, the greatest item sits at the top. Heaps guarantee exactly one thing. The top is always either the min or max value in the entire structure, meaning you can access it in constant time. A good example of a heap in action is your GPS system. It runs an algorithm called Dijkstra's algorithm, which works on a min heap. If you're looking for the nearest Starbucks, for instance, the min heap answers that instantly since the answer is sitting right at the top. In machine learning, heaps are incredibly useful as well. When a large language model picks up its next words, for example, it doesn't look at a bunch of possible tokens. Instead, it just uses a heap to grab the most likely ones. The next data structure is called the trie data structure. The name comes from the word retrieval, and it's a data structure that tries to predict what you're typing. Also known as a prefix tree, the trie is yet another tree-based data structure used to efficiently store and retrieve strings, especially when searching by prefixes. Each node in a trie represents a single character, and the path from the root to a node forms part or all of a word. Unlike binary search trees, tries organize data by characters rather than comparing entire values, making operations such as inserting, searching, and checking whether a prefix exists very efficient. For example, let's say you type CA into your phone's keyboard. The trie starts at the root, steps down to C, then to A, 2 hops. Everything hanging below that node is a suggestion: cat, car, or card. It just walked 2 letters and found all the completions waiting there. Now you know the secret weapon behind the autocomplete feature. In machine learning, tries live inside tokenizers, the tool that chops your prompt into pieces a large language model can read. Next up is a key data structure, the graph. This is one of the most powerful and flexible data structures on this list. Unlike a tree, which has strict parent-child rules, a graph is just nodes connected by edges, with no rules or hierarchy. Any node can connect to any other node, and connections between them can go one way or both. To put it more formally, it means graphs can either be directed or undirected. Graphs can also be weighted, which essentially means that these edges can store values. A good example of a graph is a social network on Facebook, which is a graph of people connected by friendships. There are 2 common ways to store a graph: an adjacency matrix, a grid where a 1 means 2 nodes are connected, or an adjacency list, where each node keeps a list of its neighbors. Adjacency lists win for large, sparse graphs, which are most real-world graphs, while matrices win when you need to check connections instantly. A special type of graph worth knowing is the directed acyclic graph, or DAG, where edges only go one way and there are no loops. In machine learning, graphs are kind of a big deal. For instance, take a look at this neural network, which is a system inspired by the human brain to improve a model's learning capabilities. What does it look like to you? That's right, a graph. It's got everything that makes up a graph, from nodes to edges to weights. The next data structure on the list is a bit lesser known. It's called the Bloom filter. Yes, it sounds more like a feature on a phone editing app than an actual data structure, but still, this one is quite interesting. Ask yourself, what if your dataset is so massive that even a hash set can't fit it in memory? The Bloom filter is the answer. A Bloom filter is a memory-efficient, probabilistic data structure that tells you almost instantly if something is in a set. It works by using multiple hash functions to map each inserted element to several positions in a fixed size array, setting those positions to 1. When checking for an element, the same hash functions are applied. If any corresponding bit is 0, the element is definitely not in the set. If all the bits are 1, the element is probably in the set, although there is a chance of a false positive. The useful thing about Bloom filters is that they never produce false negatives for inserted items. In machine learning, they're used to remove duplicates from massive training datasets. Now we've reached the final data structure on this list. And if you're interested in AI, this is the one you need to know. Hierarchical, Navigable, Small World. I know, it's a hell of a name compared to the other structures on this list, so I'll just call it HNSW. An HNSW is a graph-based data structure that helps computers quickly find items that are most similar to a given item. It organizes data into multiple layers of interconnected nodes, where the upper layers provide a broad overview for quickly narrowing the search area, and the lower areas contain more detailed connections to find the closest matches. This is the data structure powering the massive vector databases that make tools like ChatGPT so smart. Here's the problem it solves. In modern AI, we represent data as vectors, long lists of numbers that represent the meaning of an image or a sentence. When you ask an AI a question, it has to find the most similar vector out of millions or even billions. Checking every single one is impossible. The multi-layered graph structure of an HNSW fixes this. It's the engine behind retrieval augmented generation, semantic search, and recommendation systems. And there you have it, every essential data structure for programming and machine learning. From simple arrays to complex HNSW graphs, these are the building blocks of the digital world. If you found this helpful and want to go deeper, don't forget to check out the newsletter in the description, where I turn these concepts into actual code and projects every single week. Thank you guys for watching, and I'll see you in the next video.